Hello. In this video, we are going to use calculus integration to come up with a formula to find the centroid, or the center of mass, of a region on a two-dimensional plane. Here I have the result of this entire presentation right here on the first slide, just to give you a little preview of where we're going and what we'll discover in the process of this video. And at the bottom of this slide, you see 4 examples of planar regions, or regions on the plane. So the centroid, or the center of mass of a planar region, like these examples, is the balancing point. If you could imagine, for example, taking that rectangular region that I just circled down there on the bottom left, imagine that that's a piece of cardboard. And I place a really thin point, like the tip of a pen, let's say, out on a table. Where should I place the rectangular piece of cardboard so that it balances perfectly on the tip of my pen? Well, making a, I hope, pretty reasonable assumption that the cardboard is spread out in a uniform manner so that it's not heavier in one place than it is in the other, then that balancing point, that centroid, that center of mass, is precisely where you might guess it would be, right there perfectly in the geometric center of the rectangle. Now, if my cardboard had been cut into the shape of a triangle, let's say, well, that point in there, in the center of the triangle, that's the centroid, that's the center of mass, that's the balancing point. If I were to place that black dot right there on the tip of a very thin tip of my pen, the triangular piece of cardboard would balance perfectly right on that point. But for some more, let's say, exotic examples where the boundaries of the region are curved like these, as opposed to straight line rectilinear boundaries like the rectangle and the triangle, the situation is a little harder to predict. At least for this semicircular region right here, I hope you'll agree that it's pretty obvious after a moment's thought that the balancing point should be right there along the vertical y-axis, because that splits the region perfectly in half. There's symmetry. The region on the right and the left of that line is, they're perfect mirror images of each other. So it makes sense that the balancing point, the centroid, is right there halfway in between. But where is the vertical height of that point? Why is it there and not somewhat a little higher or somewhat a little lower? What can I do to figure out exactly what the y-coordinate of that point is? Well, that's what these formulas up here are going to do for us. And in the process of this video, I'm going to show you all of the steps needed to come up with these integration formulas. The reason for doing this is that moving forward, we're going to apply these formulas to calculate the coordinates of some examples. And in the next video, I will specifically do all 4 of these examples that you see outlined here on the first slide. But I do find it helpful and, quite honestly, genuinely fascinating to see why it's these particular integral formulas. I don't want to treat them like a black box that somebody just said, here they are, use them. I would like to know a little more about where they come from and why they work. And that's what we're going to do in this video. For those of you watching at home, you can pause the video and visit this Desmos link here. I'll pull it up on my tablet. And you can see the 4 example graphs that I've outlined there, and you can actually see the coordinates of their centroids, their centers of mass labeled. To switch between them, you can turn on and off all of the expressions I have boxed into a folder. So for example, if I expand the rectangle one by clicking on that little triangle there, it tells you, oh, I'm graphed a function f of x. It's the flat line y equals 2 between -2 and 2. I have shaded the region. I've labeled the point. If you collapse that region again, that folder, then you can toggle it on and off. See what I'm clicking there. And then I can turn on another one like the triangle. You can see the coordinates. I can turn on the semicircle, and I can turn on the parabola. So before we even get into, eventually, a planar region like that, let's focus on the most simple version of that problem, which is 2 points. Imagine I have 2 weights, 2 masses. To have a visual in mind, you can imagine two heavy boxes placed on opposite sides of a seesaw, and they're balancing on a fulcrum. That's the name for that balancing tool in the middle of a seesaw. Now, if the boxes have the same weight, the same mass, then from our schoolyard intuition, I think you'll agree that it makes sense that if they're the same weight, I need to place them equally far away from the fulcrum, from the center of the seesaw, from the balancing point, to make them perfectly balanced and not tip one way or the other. But what if they have different masses? What if they weigh different amounts? I obviously have to place them at different distances from the fulcrum. And if you think about it, the lighter one has to be further away from the balancing point to balance out the heavy weight of the other one that is placed much closer. I suggest pausing the video, maybe searching for a ruler and some light, slightly different weight objects in your house and experimenting with this on your own, just to try to convince yourself of this. You can try to balance a ruler on your fingertip, or maybe you can go out to the playground and go on a seesaw, but just try to convince yourself of what I just said. But as it turns out, there's a even more specific rule or formula for how far apart those point masses must be from the balancing point that was discovered by the ancient Greek scientist, mathematician, philosopher, physicist extraordinaire, Archimedes, and it's called the law of the lever. It says that the ratio of the distances of those 2 points is the reciprocal of the ratio of their masses. So, said another way, if one of the masses is, let's say, 4 times as much as the other one, then it has to be 4 times closer to the balancing point than the other one. So I've written out here a little bit of detail about that toy example I just mentioned out loud. Take this statement of the law of the lever there, which says that the product of the first point's mass times its distance from the fulcrum has to equal the product of the second point mass's mass times its distance from the fulcrum. And by dividing both sides by m2 and d1, I can see what I was outlining earlier about their ratios. In other words, like in my example here, if the first mass is 4 times as much as the second mass, then that means it has to be 4 times closer to the balancing point than the other one. In other words, see here how that's the reciprocal of the distances is equal to the ratio of the masses, and vice versa. Clicking on that or visiting that YouTube link I have down there will take you to a short little video by, I believe, a physics professor who's demonstrating this same idea using a meter stick and some stuffed animals that follows this same formula I mentioned here, where one of them is 4 times as much as the other. So that will give you a visual to have in mind as you're thinking about this example. So let's start mathematizing this stuff, so to speak. Let's assign some variables and set up a coordinate system. Let's suppose that those 2 point masses, that they're placed along the x-axis. And let's call the first one, it's at the point x1, and the second one, it's at the point x2. And let's use x bar, this x with the line over it, for the fulcrum, or the balancing point. And yes, I really would call that thing x bar. That's common in mathematics to not quite run out of letters, but want to use a variation on a letter and do something with it, like put a 0 underneath it, or a 1 or a 2, or put a bar on top. Let's now apply that Archimedes law of the lever to describe this situation and essentially solve for, get an algebraic expression for where that fulcrum should be located along the x-axis, assuming we know everything else about the point masses, where they are and how much they weigh. So we're kind of assuming here already that we know what x bar is to be able to put it on the diagram there. But essentially think of it this way in terms of the algebra of what we're doing here. We're writing all of the expressions we're about to write using that x bar, that unknown. We're writing everything in terms of it. So I'm going to use d1, the distance from the first point mass to the fulcrum, as the separation, just the subtraction, the difference between where the fulcrum is on the x-axis and where the first point is on the x-axis. And let's do the same thing. For the second point mass, its distance from the fulcrum is x2 minus x bar. Notice that the order swaps between those two because I've set everything up so that the first point mass is the one on the left, the second point mass is the one on the right, and therefore by our physical intuition the fulcrum has to be in the middle somewhere. And so that's why I have the subtraction going in opposite orders. We're going to use little m, to mean the total mass of the system. So for right now, that's just the sum of the 2 point masses that I have so far. But in the very near future, say the next slide, we're going to talk about what happens when I add more points to this system, more masses. So I'm going to continue to use little m to mean the sum of all of the masses that we're considering. Now the law of the lever says the product of the first point's mass times its distance from the fulcrum is equal to the second point's mass times its distance from the fulcrum. And here I've just written that out using what we've declared to be d1 and d2 based on the coordinate system that we've set up here along the x-axis. Now we can take what we have right here and do a little bit of algebra to solve for that fulcrum value, the x bar. That happens to appear in 2 places on this equation, but we're going to treat everything else, m1, x1, m2, and x2, as constants, and we're going to rearrange and solve this like we would any other linear equation, where the x bar is the variable and everything else is just a constant number. There I've used the distributive property on both sides of the equation there to rewrite everything as what you see down there. And now I've done a little bit of rearranging. I've taken this minus m2 x bar term on the right side and I've added it to the left side of the equation. And likewise, I've taken this minus m1 x1 on the left side of the equation and I've added it to the right side of the equation. Now, what can I do now? I'm trying to solve for that x bar thing that you see right there. And notice that it appears in both terms on the left side of the equation. So I'm going to factor that out. I'm going to undo the distributive property on that left side of the equation. There, I've done that step. I now see x bar times the quantity m1 plus m2 equals to the same right-hand side I had before. And if you just divide both sides by this quantity in the parentheses there, if I divide that underneath, you can see that that's exactly what happened to get to that final state I have up there typed. And the final little step you could say I've done is to write the sum of the 2 masses as the total, that little m. That's going to be convenient for what we're about to do in the next slide, which is generalizing to more than 2 points. Now you can take my word for it a little bit here, try to think about it for yourself. Essentially we're applying a little inductive reasoning here to say that if I had more than 2 points, that would work out pretty much the same way. If I had a bunch of point masses all set up along a number line like that, and I had their distances from the 0, the origin of the number line, labeled x1, x2, x3, all the way up to, let's say, xn. I'm going to use n as the generic number of point masses that I'm talking about. Then that same result that I had from the previous slide will apply. On the numerator, I'll have the sum of all of the products of mass times position, or x-coordinate. And on the bottom, I'll have the sum of all the masses, and that's what that m represents, the total mass of the system. And then I hope this might be a little refresher or practice with reading summation notation. This expression up here in the numerator on the right-hand side just means exactly what I have written out, an expanded form with the ellipses, with the dot, dot, dot on the left. This doesn't say anything different, it just says it in a different way. So when I say moment, this is the quantity that I'm talking about. A product like mass times coordinate like that, that's the moment of that first point mass. It measures how much that mass tends to contribute to the system's tippiness around the origin. So let's jump back to the previous slide. Look at that first point mass right here. It is to the right of the origin, x equals 0, and so if I make that point further away, if I move it to the right, then x1 will get bigger, and that will cause the system to tip away from the origin. It will make it less likely that the origin is the balancing point. Likewise, if I make m1 bigger, if I make that mass larger, that would also serve to make this whole system tip away from the origin. It makes it less likely that the origin is the fulcrum, the balancing point. And so having that product of m1 times x1, that measures that tippiness. If either one of those quantities, the mass or the location, increases, that serves to increase that product, and it will say, hey, your system is more tippy around the origin. And so we're going to call that the moment for that point mass. So what you see up there in the numerator is the sum of all of the individual moments. It's the total moment of the system. And just to remind ourselves that we're measuring everything around x equals 0 along this number line, we're going to say it's the total moment of the system about the origin, or across the origin, or around the origin. That's telling us that we're measuring the tippiness around that specified central point where x equals 0. And so if I call that capital M for the total moment, then another way to say this equation up there at the top is that the x bar is the total moment of the whole system, that's the summation on the numerator, divided by little m, the total mass of the whole system. And I've just written that in a slightly different way down here by multiplying through on both sides by little m. But I did that to show you that this is pretty similar to the law of the lever, which says something about mass times distance. So one way to think about this now is that if I took that whole system with a whole bunch of points, I can equivalently treat it like all of their masses had been gathered up and collected into one giant mass, one giant weight, and placed at the fulcrum, at the centroid, at the balancing point. If I take all of the masses that were spread out along the number line and combine their weights and place them at this calculated centroid point, then that system will behave in terms of its tippiness left and right as the same set of those endpoints spread out around. So everything we've done so far has been one-dimensional on a number line. Turns out not a whole lot is different if I add a second dimension and we talk about point masses on the two-dimensional Cartesian plane. Let's say I have a point mass with mass m sub I at a point on the Cartesian plane, so it has two coordinates, xi and yi. If I have a bunch of those things, where is the center of mass on the plane? Well, here's the thing. We can do this in the x direction, left, right, horizontally, in just the same way that we were doing in all of our previous work. And we can measure this centroid, the center of mass, vertically, up and down along the y-axis, in the same way, but using the y-coordinates instead of the x-coordinates. In other words, we don't have to invent anything new, we just have to do everything we've done so far in the two standard directions, the x and the y directions. So we're going to use, now bear with me because this notation may seem backwards momentarily, but it will make sense in retrospect soon. We're going to use my to mean the left-right x direction tendency, the tippiness of the system. So why am I using y if I'm talking about x coordinates, if I'm talking about horizontalness, if I'm talking about left-right tippiness? Well, I'm using y because we're going to measure that across x equals 0, which is the y-axis. That's why I'm going to use that m sub y, because it's across the y-axis. Imagine that vertical y-axis as the central line that I'm measuring across. Then m sub y, the total moment of the x-coordinates, the tippiness left to right, is across that vertical line. So the previous result we were just looking at tells me that the total mass, the little m of the system, times whatever the correct x-coordinate of the center of mass is going to be, will equal that total moment. So on the previous slide, we wrote this as just m without the little sub y. I'm going to use the subscript y now to remind myself that this is based on across the y-axis where x equals 0. And very similarly, let's talk about m sub x, the total moment across the x-axis. Imagine doing all of the same discussion we were just doing, but kind of rotate your screen 90 degrees, look at this by talking about y-coordinates and measuring them, their tendency to tip across this horizontal line, the x-axis, the y equals 0 line. And so by the same analogous thinking, we could say that the total mass of the system, m, times the y-coordinate of the center of mass, whatever that's going to turn out to be, will have to equal the total moment of the system in that direction, which is across the x-axis, and that's why we're using that subscript x. So after all this, here is the main conclusion from what we know so far. The center of mass of this system of some finite number of point masses can be found by calculating the individual total moments in both the y and the x direction, or said another way, across the x-axis and across the y-axis. Let's apply this result to a specific example. Now I've set up something here where I've looked at 3 point masses, and I'm telling you their masses right here, 4, 10, and 6, and I'm telling you their coordinates here. The first one's at 0, 1, second one's at 2, 4, and the third one's at 4, 0. And I've tried to scale and size the circles in the diagram you see there to be related to their masses. So you can see that second one is a little bit more than twice as big compared to the first one, because its mass, 10, is a little bit more than twice as big as the first one, 4. So just to give you something to think about. But in terms of the logical thinking we just went through in all the previous slides, I would really be imagining that all of the mass is concentrated at the center point and not spread out along the circle like that. I've just given you those circles to help you realize that there's a bigger mass over here, there's a medium one over here, and there's a small one over there. But for each of them, pretend that the mass is all concentrated right in the center point. So you can also click on this Desmos link here, which will take you to this graph, and you can see, if you want to, you can expand all the formulas to see the work I've done to put together this example. And you can also see the coordinates of the center of mass. That's the orange point, the 2.2, the 2.2. But you can also click and drag on this dot and try to guess for yourself where the center of mass should be. I think you can convince yourself that it shouldn't be down here because of that very, very heavy mass in the top, the green one. It should probably be a little bit higher up than it is down low because of that heavy mass up there. Also should be pretty far over to the right because this is this is a small mass, the red one, and these are two very large masses, the green and the purple one. So the center of mass should be somewhere further to the right and somewhere higher up. Why it's exactly those coordinates 2.2, 2.2, that's what we're about to calculate together. So let's apply the formulas that we were just looking at. That's what's in the box here that I'm about to draw. Remember that little m is the total mass, so that's going to be 4 plus 10 plus 6, that's going to be 20. The total moment about the y-axis, or across x equals 0, that's why I'm using the y subscript there, that's going to be based on the x-coordinates. And meanwhile, the moment about the x-axis, about the y-axis, or across, there we go. Just caught a little typo in my copying and pasting efforts here. The moment about the x-axis, or across the line y equals 0, is going to be based on the y-coordinates of the points. So on the next slide, I have all of those calculations. I suggest you pausing the video, doing it for yourself, and then pressing play again to check your work with what I am about to show. Here we are. Here are the results of that. The moment about the y-axis, you can see I have the three masses, 4, 10, and 6. And then you can see I have the x-coordinates to measure the moment about the y-axis. There's the 0, the 2, and the 4. And you can also see I'm using the y-coordinates of 1, 4, and 0. to measure the moment about the x-axis, across the x-axis where y equals 0. And then you can see those totals. Now I happen to cook this all up so that they both are exactly 44. That does not always happen, not at all. This is just a quote-unquote coincidence for this example. And there's the total mass of 20 that I mentioned on the previous slide. And then here I am calculating the center of mass, the coordinates of the centroid, based on all of those values we've just calculated. And it turns out they're both 2.2 because they have the same moment, 44, and then there's the total mass of 20. And that's the coordinates of that point right there. That's the balancing point. If I actually had these three masses placed on a cardboard cutout triangle, and I had really small ball bearings with these weights placed on the corners of the triangle, that right there is the point that I would want to balance on the tip of my pen to get this to perfectly balance flat. So the next thing we're going to do is talk about generalizing from not just a finite number of point masses to an infinite number of points, really, a planar region, a solid region on the plane. Let's say I'm talking about a region that's bounded underneath the graph of some function y equals f of x, and above the x-axis y equals 0. So I'm talking about a region kind of like what you see here, this semicircle. And let's say it's bounded between two x values, x equals a to b. So in this case, like that's a and that's b, and this is the graph of f of x, let's say. The key step that we're about to do is one of the major themes of calculus, which is let's slice this planar region into a bunch of rectangles and say, well, you know what, that's not a perfect estimate of the region itself, but maybe it's good enough for what we want to do. And then we'll talk about what would happen in the limit as I let the number of rectangles go to infinity, or I let their uniform widths decrease to 0 at the same time. Essentially what we're going to do is take one of these rectangles and think about how that rectangular region, although I admit it's not a perfect approximation to the region itself, the planar region in green there, but in the limit, as I make those rectangles thinner and thinner, then what I'm doing would become a better and better approximation. So let's think about what this rectangular region right there, how it contributes to the moment around the y-axis and around the x-axis. In other words, what contribution does this rectangle make to the center of mass? So the first insight we're going to make is that each rectangular region, like the one I've drawn there, we can treat it as if all of its mass is located at its center of mass. And this is where I then get to use the insight which says the centroid of a rectangle is where you would expect its geometric center. So that's why I've drawn that dot right there, right in the perfect middle of a rectangle. Again, I know that the rectangle is not perfectly approximating that curve because I've drawn it so big, but imagine in the limit as I have a ton of really thin ones, then it's not so bad of an estimate. In the limit, it becomes better and better. So we're going to pretend that all of the mass of the rectangle is located at that geometric center. Let's talk about what that center point is and what its mass is. So we're going to assume that the rectangle is located at some arbitrary x coordinate, where x is between the a and the b boundaries that we've established earlier. And we're going to say that the height of the rectangle is based on the function value of f at that x coordinate. Again, that's not a perfect estimate based on what I've drawn here, but in the limit, as these rectangles get thinner and thinner and thinner, that's going to be a closer and closer approximation. And so it turns out that center of mass of the rectangle has these coordinates, x comma 1/2 f of x, because that's the geometric center of that rectangle. I've chosen its x value to be right in the middle, and its height is f of x, so halfway up the center is 1/2 f of x. And then for the mass, here's where I start to introduce this concept of density. Let's assume that the planar region has all of its mass spread out uniformly, so it has a constant mass density of rho. That may look like a little p, but that's actually the lowercase Greek letter rho. It is very commonly used as a notational symbol in physics for mass density or other kinds of density like this. So when I say let's treat each rectangle as if all its mass is located at its own center of mass, well, I can actually write down what the mass of the rectangle is. In general, the mass of something is its density times its area, as long as that density is constant, like it is for the assumption that we're making here, that it's constant. So in this case, that density is rho, and the area is, well, I have a rectangle whose width is, well, here's where I have to go back and relabel that rectangle a little bit. I said x is the x-coordinate of the center. The width of that rectangle, we're going to use this infinitesimal dx. Because remember, I'm imagining this process where I keep doing this and making the rectangles thinner and thinner and thinner. So I'm going to say that the width of each rectangle is that infinitesimal amount dx. So when I see area down here of the rectangle, it's going to be width times height. And that's the mass of the rectangle, the density rho times its width dx times its height f of x. Knowing also the coordinates of that center of mass of the rectangle, I now have everything I know, everything I need to know to write down the contribution of this rectangle to the moment around the y-axis and around the x-axis. So when I say up here, the moment about the y-axis, remember to think about the y-axis as the vertical line x equals 0, which is why I'm talking about the left-right horizontal x contributions of this rectangular mass to the moment. So when I say m times d, I mean the horizontal distance. And even more specifically, I mean the horizontal distance from the rectangle to the y-axis. And again, even more specifically, by rectangle, I mean that point at the geometric center of it, its centroid, its own center of mass. So what's the horizontal distance from that point over to the x-axis, the y-axis, where x equals 0? Well, that's exactly what the x-coordinate of that point is. That's exactly what x is. So when I look ahead again on the next page, that mass there I've written, for the mass there I've written rho times f of x times d of x. That's the mass we got on the previous slide. And then that horizontal distance is x that we just observed by looking at the center of mass of the rectangle and comparing it to the y-axis. And then I'm just reordering the products of those terms there to write it in the way that we have over here, where the dx is written at the very far right, because we're about to put that into some integrals down there. For the moment about the y-axis, well, I have the same kind of result. I have the mass there in yellow times, now the distance, I mean the vertical distance from the rectangle to the x-axis. So let's look back at the previous slide to see why that's 1/2 f of x. Well, there you go. That was exactly the height of that center of mass point. It's halfway up the rectangle to its total height of f of x. That's the 1/2. And here I've just rewritten some of the terms. I've got the d of x on the far right, and you may have noticed that there's 1 f of x there and 1 f of x there, and that's why I have all of that squared. So if that's the individual contribution from one of the rectangles to these total moments, well, the integration comes in by imagining summing, just like we had in the earlier slide where I had n point masses and we just added up all of their individual moments. We're doing the same thing here. We're summing a whole bunch of individual contributions, imagining a limit as that width, that very infinitesimal thickness dx goes to 0, and that's exactly where the integral comes out. You might recognize the same kind of thinking from chopping up a two-dimensional region into rectangles, the Riemann sums, when we first introduced integration. Or even a couple of videos ago where we talked about Hooke's law, a changing force, and how to calculate the work or energy required to work against that force as it changes. The same idea of chopping it up into small pieces and summing them together, like we're doing here. The only other thing I need is this little m, the total mass of the region, which is, as I said before, density times area. And what is the area of the region if not the integral of the function f itself between x equals a and x equals b? That's where you see this stuff written in the denominators of these expressions. And hey, lo and behold, after all of that, turns out that that density didn't matter. What really mattered to us was that it was constant. That allows us to do all of these simple things that we're doing. I don't even want to get into how we would have to deal with a density that's changing over the region. Assuming it's constant makes all of this even more manageable. And so canceling those things out and just saying A, the area of the region, and not writing that integral again, that allows me to state them in the way that you see down here at the very bottom. And that's exactly what I had way back on the first slide, if you want to look back and see that. And now we know where all of that comes from. In the next video, we will apply these formulas to a few examples, including these very four down here, the rectangle, the triangle, the semicircle, and the parabola. And I'll even do one further example where the region is bounded between not a graph and the x-axis, but between two different curves. So skip ahead to the next video to see that.